Good morning, dear sir and madam. My topic is radiation hardened processors, and my name is Krishiv Modi. So now let's begin the PPT. Ensuring reliability in extreme environments. Introduction. Radiation hardened processors are specially designed microprocessors that can operate reliably in environments with high levels of ionizing radiation. These processors are essential for aerospace defense and nuclear applications, where failure due to radiation could be catastrophic. The space environment. Space is filled with radiation sources like cosmic rays, solar particle events, and Allen belt particles. Electronics in satellites and spacecrafts are constantly bombarded by high energy particles, which can corrupt data and damage circuits. Key radiation sources in space. The first is solar particle events, which is SPEs, caused by solar flares and coronal mass ejections, that is CMEs, emit protons, electrons, and heavy ions at very high speed, can cause short-term radiation spikes, damaging spacecraft electronics. Galactic cosmic rays, that is GCRs, high energy particles originating outside the solar system, consist mostly of protons and heavy ions, penetrate deep into materials and can cause cumulative damage over time. Effects of radiation on electronics. Radiation can cause multiple issues in electronics, such as total ionizing dose, single event upsets, single event latch-ups. So we will talk about total ionizing dose, which is TID, causes long-term degradation. Now we will talk about single event upsets, which is SEUs, flip bits into memory or registers. Single event latch-ups, which is SELs, can cause high current states, potentially destroying components. What is radiation hardening? So, radiation hardening refers to the design, techniques, and manufacturing processes used to ensure electronic components can withstand radiation exposure. This can involve changes at the circuit level, architectural level, and packaging level. Types of radiation hardening. There are three main types of radiation hardening are used: hardening by design, hardening by process, hardening by shielding. So the first is hardening by design, which is HBD, redundant circuits error correction. Hardening by process, which is HBP, special materials and structures. Hardening by shielding, which is HBS, which is physical barriers to radiation. Now, now we will talk about hardening by design. So, HBD involves circuit level design improvements like triple modular redundancy, which is TMR, to vote on correct outputs, error correction codes, which is ECC, for memory protection, watchdog timers to reset systems after faults. Hardening by process. HBP focuses on the semiconductor manufacturing process. For example, use of silicon on insulator, which is SOI technology, to isolate components, enclosed layout transistors to minimize charge buildup. Now, process modifications to reduce susceptibility to SEUs. Hardening by shielding. This approach adds materials around components to block or attenuate radiation. However, shielding adds weight and space, making it less ideal for aerospace applications. It is often used in conjunction with the other hardening methods. Key features. Radiation hardened processors often include ECC protected memory subsystems, built-in fault detection and self-checking logic, operability over wide temperature and voltage ranges, redundant data paths and code units. Popular processors. Some widely used radiation hardened processor, which is RAD 750, Leon series, ARM Cortex R family, custom RHBD S6. We will talk about RAD 750, which is base systems, power PC architecture used in Mars rovers. Now we'll talk about Leon series, which was created by Cobham Gessler. Spark-based used in ESA missions. ARM Cortex-R family. Some variants made radiation tolerant. Custom RHBD ASICs. Application-specific chips for critical systems. Okay, let's move on. Case study on RAD 750. So, RAD 750 is a radiation hardened version of the PowerPC 750 processor. It can withstand up to 1 mRAD and operate in temperatures from 55 degrees Celsius to 155 degrees Celsius. Used in Mars rovers, it demonstrates high reliability under extreme conditions. So, here's the case study for Leon processor. The Leon family are Spark C V8 based processors designed by Cobham Gessler. They include built-in TMR and error detection logic, widely adopted in European Space Agency missions due to their open architecture and reliability. Here's the case study for ARM Cortex-R family, red tolerant variants. Overview. ARM-based real-time processors adapted for space. R-series processors are used in automotive and industrial, and red-tolerant versions have emerged for aerospace. Examples: Cortex R4, R5, R52. Some variants made radiation tolerant by vendors like Honeywell and STM Microelectronics. Features: deterministic real-time performance, lockstep mode for fault detection, lower power consumption, why it's growing, modern tool chain and developer ecosystem, easier integration into hybrid commercial and military systems. Case study on RHBD ASICs, radiation hardened by design custom chips. Overview. Custom application specific integrated circuits, ASICs, built from the ground up with radiation immunity in mind. Who uses them? NASA, ESA, DoD, Boeing, Lockheed Martin. Often classified for military and strategic missions. Its pros are extremely reliable and tailored, can achieve higher radiation tolerance than commercial chips. Its cons are long development time, high cost, limited flexibility. Now, there is a comparison between RAD 750 versus Leon 3. So, the RAD 750 has higher radiation tolerance, commercial heritage. Now, the Leon 3 has open source, configurable, well suited for softcore FPGA use. Each has advantage depending on mission and cost constraints. Applications. So the applications of radiation hardened processor are radiation hardened processor are used in satellites and space probes, military avionics and ground systems, nuclear power plants and particle accelerators, high altitude long endurance hail drones. Design challenges. So there are certain designing challenges for the radiation hardened processor. So designing radiation hardened processors come with hurdles, increased cost and complexity, longer development and verification cycles, performance often lags behind commercial processors, limited foundry options, and production volume. Emerging technologies. So there are certain emerging technologies for the radiation hardening processors. So they are new approaches in the field include using commercial off the shelf, that is coats components with mitigation techniques, FPGA based designs for reconfigurability, AI enhanced anomaly detection and correction mechanisms. So the future trends shaping the future include miniaturization and integration of red hard components, machine learning for predictive fault tolerance, quantum and neuromorphic processors for advanced mission capabilities. Now, the summary for radiation hardening processors are indispensable in environments with high radiation exposure. They are designed using various techniques to ensure mission success in critical operations. As technology advances, their capabilities and efficiency continue to grow. Thank you very much. Here's my PPT for radiation hardening processors. Thank you so much.